So let's talk a little bit about you guys. Who here is writing C++ on a pretty regular basis? Quite a few people, not everybody though. All right. Who here is familiar with modern C++, so C++ 11 and beyond? Yeah. The same sort of people. Is anybody here using C++ 17? One? Cool. So when I talk about modern C++, we're referring to things like R values and move semantics. And when I say move semantics, I'm talking about moving the ownership of an object, not actually moving the object in memory. And also about lambdas, perfect forwarding when we start templating with R values, that sort of thing. And so we'll look at a couple examples of this later in the talk. So one of the things... Yep. Ah, right, pizza count. I forgot the pizza count. My bad. So who wants pizza? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and me, 14. Anybody that is vegan, gluten-free? One vegetarian, vegan. All right. Good. All right. Sorry about that. So one of the things that I like about working at Edument is we have quite a big balance of things. So we do teaching and consulting. We also have time for personal development. And so we are supposed to operate on a 60-20-20 split. So we spend 60% of our time doing billable work, 20% of the time doing things to improve the company in some way, like writing new courses, that sort of thing, and 20% of the time developing ourselves. And so on the side for my 20%, me and one of my colleagues, Eric Mann, who's unfortunately not here tonight, are working on an AR Rubik's Cube solver. So neither of us know how to solve a Rubik's Cube, and instead of learning to solve a Rubik's Cube like a normal person, we've decided that instead we'll write a program to do that for us. So here you can see an early prototype of it. You can see that we're detecting the different colors of the different squares from the camera. And we're not using ARKit or ARCore for this. Both of those are very good at finding planes that are horizontal, but we want to find planes at all different angles. And so we use OpenCV, and we can very quickly detect points on a plane and create planes in any direction from that. So we'll talk a little bit about the C++ 17 features that have been released, and then we'll go back to the Rubik's Cube and use it in our examples. So C++ 17 releases quite a few new language features. We have type deduction for template classes. Previously, we saw people doing things like having a factory template function, and we would use the template function to do type deduction and return the class from that. And now we can just do it directly with the class. So we have type deduction. We don't have to specify it. We get const expressions for lambda capture and const expression if. So these are things that help us to have more done at compile time. And as we all know, the more things we can do at compile time, the better performance we can have later. We also get nested namespaces and a bunch of other features that would fill up the rest of the wall if I tried to put them all here. In the C++ 17 standard library, we have a bunch of new features. There's more than this as well. We have string view. So string view is a read-only type. So if your function is taking a string and not mutating it, you can use a string view. It's essentially a pointer and the size, so it's very cheap to pass around. And it means that we can go through and use that string without mutating it. And it becomes very obvious to a caller that we're not going to be mutating the string. We have standard variant, which is a little bit like a type-safe union. And we have standard optional, which we'll be talking about quite a bit tonight. So I'll leave that for a bit later. Right? So who here has ever taken apart a Rubik's Cube? Has anybody, you have? Anybody else pulled apart a Rubik's Cube? So how is a Rubik's Cube built? Well, inside of a Rubik's Cube, we have cubies. So if we pull it apart, I broke one on my desk the other day, so we could take a nice picture. And so each cubie has a face, or multiple faces. So we can see here, this is a center cubie from right here, and it has one blue face, and this one is an edge cubie, it has two faces, and this one is a corner cubie with three. And so we have these across the whole Rubik's Cube, right? So when we write this in code, we can quite easily translate this to something like a map where we have a face and the color, and which face it is will be dependent on when we scan the cube at the beginning, which face we should be using. And the color we can put in an enum class as well. So here we're using the more modern enum class, which means that it won't automatically fall back to integers. It's strongly typed. And so this means that we can get things like compiler warnings. So for example, if I write a switch statement and I only cover half of the classes, my compiler can warn me, hey, Steven, you covered green, red, and white, but you forgot these other ones. So, what if I don't have a default? Like, what's going to happen? You can pick up on things easier, and you don't have to just catch them in code review. In addition, because they don't just fall back to integer, if I try and multiply them, like if I have green times 2, or something like this, or if I try and do addition, like green plus red, I will get different errors unless I actually define for the class the types and how I want those operators to work. So this gives me a lot more safety than if I'm just using raw enums. So today when I'm reviewing code, if I see people using the old C-style enums, usually I flag that as something that should be changed in the code review, or at least should be explained why they're doing that. If we want to get the underlying type, we can of course use toUnderlyingType and actually extract that ourselves. So if we think about how our color map would look, for this QB we would have an up face and blue, because when I scanned it, it was on the upper face, imagining it was in this orientation. For this one, we would have up is blue and front is red for this one. And here we have up is yellow, front is red, and right is green because it comes from the corner here. We'll use this one for most of our examples tonight as we just discuss through things. So when we go to solve the Rubik's Cube, we often need to ask the cubies what color they have on which face in order for us to run through our algorithms, right? So we have a function something like this. So we return a color, and we say get color of face, and we pass in which face we want. It's a const function because we're not changing anything inside. Here we can see that we do map.find. We use map.find instead of the indice access, because with the indice access, if we access a face that's not there, it will actually create it in the map with an empty spot. So that's not quite what we have in mind. And if we're not at the end, then we know that we found a color, so we return it. But we're left with the classical problem of what do we return here? Right? We have to return something, but the question is what? So who has suggestions for something that we can return here? Some different ways to solve this problem. Yep. Yeah, so we could have an unknown, some other options. All right, so the first option, we can have an unknown of some type. We can put it at the beginning or the end. It's quite common to have it at the beginning. Here I've put it at the end because I added it after I had made the rest of the enum. Here I have color missing. Color unknown is maybe something different. If our scanning algorithm can't find every color, maybe it marks some as unknown and we can go and put those back. Note that this is specific to the enum class, because, for example, if we had something like that was returning an integer, it's common to see people returning -1 or something like this, but realistically, -1 is still a valid integer. And so one of the downsides of doing things like this is that it doesn't cover every case. So like if we have an integer type that we're returning, that every integer is valid, obviously if we start returning -1 from a function, and somebody expects -1 as a good answer, then we have problems, right? But if we do it like this, we end up doing it like this. We return color missing here, and this is our new function. And when we want to try it, we do something like this. So I set up a test QB here. This just initializes our map inside the QB. And then here I use the new range-based for loops, and I just run through down and up. And of course, down won't be found, so here it will print out that it did not find that one through the enum value, right? Any questions about this? So as I've said, we have some downsides. We need to handle the special cases. One of the other things that I mentioned earlier is that now I get compiler warnings because my enum, if I don't handle it everywhere. So now everywhere I need to handle this missing value, even though it's potentially valid, or maybe it's only here that I use the missing value, but everywhere that I handle colors in some way, I need to handle the case that maybe it will be missing, right? Not just when I get a color. And it doesn't work generically. As I said, if we have like integers or a string, an empty string is still a valid answer, things like that, right? So another thing that I could do is I could throw, right? So I could just throw an error here, and when I use it, I can catch that error. So I go through and we have more or less the same function. We just return our color here, and we throw if we don't find the face. And this face not found is just a small class that I made that inherits from standard exception. And so I can catch that quite easily. So when I do that, I have code something like this. So I have a try block. I try and get my color. If I get the color, then I print it out and do whatever else I would need to do with the color there. When I catch by const reference here to avoid having an extra copy constructor called. And so this is the kind of best practice according to the ISO C++ committee. And so we catch like that. And when we catch, we can print out I have a get face inside of my class that I made, which can print out the face. So this allows us to try our different ones, and we can quickly see. But we can imagine that this is quite a bit of boilerplate, right? And in many places, you're not allowed to use exceptions. Quite a few company policies and things will not allow using exceptions. Typically, exceptions are very slow, exceptionally slow. My good joke. And we have large binary sizes as a result. So because of the way that the compiler builds them, we typically end up with large binary sizes when we have exceptions, especially if we use them in a lot of places, right? Another option that we have is we could return a unique pointer, right? So who here has used unique pointer? Quite a few people? Yeah. So unique pointer is an RAII managed memory type. So its resource acquisition is initialization. So when we create it in the constructor, it will allocate the memory. And when the destructor runs, it will automatically free the memory for us. So we don't have to worry about freeing it. You could do the same thing with a raw pointer, but then you would need to remember to delete it afterwards, kind of thing. So here we just find it. We use make unique, which is new in C++ 14. If people haven't been using it. So we make a unique from it and return that, and otherwise we just return null pointer. And we're using the strongly typed null pointer here so that we can pick up errors that we wouldn't get if we were using just null or 0, depending on how we define null. So when we use it, we get some code something like this. So we go through, we find our QB. If it's found, then we dereference it, use the color. Otherwise, we say we didn't find it. So some potential problems with this. Well, null pointer can still be a valid state for some operations. Having a null pointer is not the same as saying we didn't find something. So in this case, we're giving it a special meaning, and that's perfectly fine in this case. It's acceptable. But in some cases, maybe we want something that can return both a pointer and null pointer and some other errors. And so that becomes a little bit difficult with this, right? We have possible undefined behavior. If somebody decides to dereference that null pointer without checking it first, we can have undefined behavior. It can be difficult to troubleshoot that depending on where it happens. It's a little bit unclear. The intent isn't very clear. So if I am using some library that has a function that returns a unique pointer, can that fail? Am I always guaranteed to get that back? Do I always need to check it? What is the kind of expectations, right? And memory management, if we're using a raw pointer, obviously we'll have to remember to delete the raw pointer afterwards so that we free up that memory. But in this case, it's somewhat mitigated by unique pointer. Also, because we're doing dynamic allocations, we can potentially run into more exceptions, that sort of thing, right? So another option, we could return a tuple or a struct. Has anybody used tuple? A couple of people, yeah. So when I return a tuple, I can specify the types that I'm going to return. And then here you can see I make a tuple and I put true. And so in this case, my Boolean is going to indicate whether or not I found a value. And I return my found value. Here I return false. And I needed to put something here in order to return it, right? And so now I put green because that was the first thing that IntelliSense suggested to me. But right away we can see some potential errors with this, right? So when we go through, we use standard tie. So we attach found and found color. And then if we have a found, then we can use the found color. Otherwise, we just print out that we didn't find it. Obviously, this has a lot of potential for error later. You know, maybe somebody new joins the team and they're like, oh, we have a found color, and they just use it directly and forget to check the found value. And then it becomes really difficult to troubleshoot because they're going to get green, which seems like a valid value, but maybe now somewhere deep in our algorithm for solving the Rubik's Cube, we're getting a green where really something is red, and that means that the cube is an invalid cube, right? And so we want to actually be very careful about doing this sort of thing, right? So as I said, we have a bunch of downsides. It's not enforced. We have to be careful. This is the kind of thing that we'd have to really be strong in code review to find and have our colleagues kind of catch our back for us. We're still returning a default value, and it's going to require a lot of good documentation. The intent isn't super clear. Is that Boolean saying that that item is found, or is that Boolean indicating something else, that maybe it is a valid cube or it's something else, right? So that Boolean could be anything. So this brings us to standard optional, which is new in C++ 17, and what we're going to discuss a bit more tonight, right? So here we have standard optional, and we specify what type it's going to use. And we return make optional with the type, and otherwise we return a null opt. Right? Has anybody used standard optional? Yep. Did you like it? Yep. Boost optional, yeah, also a good option. A lot of things end up in boost before they end up in the language. So here we can see how we write this. So we build up our QB here, and we run through our tests. And here we get the color of the face. And if the color exists, we can just do a Boolean check on the standard optional. And then if it's found, we can use color.value. There's also a dereference that you can use here as well. Another nice feature is you can use value or, and then you can specify a fallback, things like that, which can be quite handy. And so this is quite well designed to do exactly this, right? So the intent becomes very clear. It's very obvious that this may or may not return a value. It's obvious that we need to check it in some way. If we forget to check it, we get a specific exception when we forget to check it, which means that if we get that exception, we'll be able to debug our code very quickly because we'll see that we got a specific exception when it failed. We can also construct in place. There's an in place call that you can use. So when you do the make optional, you can actually pass in standard in place and then pass any arguments to the constructor, and they'll be passed directly in so that it can be built in place and save us a bit of copying and stuff, right? So one of the big downsides here is that it's obviously not available until 2017 C++. And as I mentioned, we're working on building this AR project, and it's on Android, which is still stuck at 2014 C++. So this gave us a bit of a problem, and we thought, it would be really nice to use this thing that we talk about in our classes and that we discuss with students. And one of the things that's nice is when you're using those things, you can, speak from experience when you're teaching a class. But unfortunately, we can't because it's not available. And so one of the things that kind of came up is we could do something different. And you're probably all thinking, okay, he said it was going to be a C++ talk, and now he's going to talk about JavaScript. And yes, it's a bit of a trap. So one of the other fun things about working at Edument is that we get to work with a lot of different technology. So myself, I teach classes on C++ and JavaScript. Occasionally, I do some consulting with Java. I use Docker quite a bit. Actually, related to the AR project, when we first had our CI pipeline set up, it took almost 45 minutes to run because we need a custom version of OpenCV, and we're running in Travis. And so we actually built a Docker container that has all of that, and using the builder pattern to make the container as small as possible. And we actually cut our build time for running the unit test to just build what we actually care about and run the unit test. We cut that down to about 1.5 minutes, just under 2 minutes from 45, which is a pretty big savings, right? And so it's kind of fun to be able to take like things that you see in other technologies and steal them and use them in a different context. So one of the things that you end up doing is you borrow these different ideas from different contexts and bring them to something else. So in Java, when people are programming in JavaScript, is anybody here JavaScript programmers? A few people, yeah. Some shaky hands. So when people are programming in JavaScript, there's some kind of typical workflow. So often we have some source that we write in ES6 or JSX or the newer like ES 2017. JavaScript naming is kind of funny. They started with numbers and then switched to years, and they skipped some numbers in the middle. So there's a bit of funny business going on there. But you want to use the latest version of the language, and then they transpile that into ES5, generally speaking, which most browsers support. And then from there, they often compile it into one file and then make that file smaller to kind of help with network issues, right? But this is the step that we're interested here in, is being able to kind of steal this idea of compiling from one to the other, right? And I also mentioned polyfilling. So what is polyfilling? Well, strictly speaking, polyfill is a brand of white stuff that you stick in your wall when you have holes in it. But in a JavaScript context, it's a little bit different. Generally speaking, we want to fill in any missing browser features. So if a browser doesn't have support for some specific feature, we kind of silently fill that in and give a nice level base for us to build off of, right? And so then we don't have to really worry about which things the browser supports and which things it doesn't. Instead, we can just use those directly, right? And the polyfill will be there if we don't need it. So how do we do the same thing in our code? Who has some ideas? Anybody? Yep. So there's some macros we can use to do that, and then we can fill in the things that are missing with templating, right? So if we look at how we can create standard optional as a template, well, we can start out by just creating a class for standard optional, and here we define a couple of types. So this is the new using syntax. It's basically doing a type def. It just comes out a little bit cleaner, so we can use that throughout our template, and we can also use it with templates. Here is how we create null opt. So here we create a null opt type, and then we define null opt as an instance of that type, right? And here we have make optional. So we take our template. Standard decay here is going to remove CV qualifiers, so const and volatile, and also things like references. And then we have standard forwarding here. So in order to prevent R values from collapsing into L values, we need to have standard forward. So when we see the ref syntax in a template, we know that we need to have standard forward here as well. Has anybody been using templating with standard forward? A few people? Yeah. So when we get values here, because of the way that type deduction works, inside of here, the R value will be an L value reference to the R value. And so then if we don't have the standard forward, it'll collapse into the L value, right? So we end up with just a reference. So we need to put this here to make sure we get that. Here we can see an example using variadic templates. So here we can get a variable number of arguments, and we use that down here. So here we have in place as the first option. So this indicates that we're going to do an in place build. And then we forward all the arguments that were passed in, because they will be the arguments that need to go to the constructor of this type, right? And once again, we have standard decay to get rid of the extra things, right? So let's take a look at the code a little. Is that big enough? All right, so yeah, we start out by just creating our null opt type and creating a null opt from that. And then we create an in place type and create an in place from that. And so that just means that we can do kind of tag dispatching the same as we normally would in templating to select ones if we want. So then we go in here and we have our normal constructors, both for an empty constructor and from a null opt. And we have then we have our copy constructor here. So if we're copying one optional into another, we need to have that there. And we have our copy assignment operator. So we just can copy from one optional into another, right? And then here we have our move constructor. So have people been writing move constructors before? A few people? Yeah. So when we write a move constructor, we steal the data out of the other object and we leave kind of an empty husk behind. And we have to keep in mind that that other one, its destructor will run, so we need to make sure that we, if we have pointers in there, for example, we set them to null pointer or something valid so that it doesn't clear out our data afterwards. But we're moving the ownership, remember, not moving the actual data. And here we have the move assignment operator, a little bit similar. We have to remember, of course, it's really common I see in our classes that people forget this line because they do x equals y and say, oh yeah, it works, great, and they move on. But if you don't have this line, then you can't do something like x equals y equals z, right? And so it's important to remember to return this pointer. And then here we see when we actually create our type, we actually need to have a separate type name here because otherwise we run into problems with constness of the objects when we're trying to create them. So it's just a little trick here to be able to handle that. And then we just forward into the storage type. So we create the new storage type and just create it from this. And so this is the same as having T2 here, or T rather. And we have our destructor, so we can clean it up. We have reset, which is one of the functions that is specified in standard optional, which basically just resets the optional to be empty again. So we just call the destructor and set has data to false. And then we have our Boolean operator, because of course we want to be able to just do if this exists and be able to get that directly. And then we have our access operators so that we can access. So we have our dereference and our arrow operators here. And then we have our actual value operator, which is the one that we saw I was using in the slides to get the value of it as well. And then we can see the private data. Here we're just using a line as and a line of so that we make sure that we align everything correctly when we create it, right? And so we end up with something sort of like this. And then we have our actual make optional functions to both create a normal one and also if we want to do in place and is very similar to like in-place back or some in-place back or something like that on a vector if you're used to using that, right? So some limitations. We need to be able to compile this. So like when we're taking this approach, we can't build things like move semantics in our values because obviously I can't template that in to the language. So it's a bit tricky if you're trying to work with something that's pre-C++ 11 and then trying to bring in C++ 11 features. You need to be a bit careful. Some things you could do, for example, lambdas you could bring in because you can make those as functors, but it's a little bit tricky to be able to replace all of that, right? So generally speaking, we can polyfill library features, and we can't really polyfill compiler features using this method. There are, I assume, other methods that you could take, but I haven't looked into it so much myself. I haven't shown here, but we can do automatic detection via the preprocessor. So, for example, we have the has include, that sort of thing, and we can go through and replace them with that, and then we can automatically fall back if we need to, right? So you don't have to do all the work yourself. When I was actually researching for this talk, I found out that I wrote all of these templates for nothing because somebody else has done it as well. So if you're looking to bring in C++ 17 features and you need them, there are some headers available, and they're header-only libraries, so you can just pull them into your project and compile them, and they have the automatic fallback built into them as well. So that's quite handy. Has anybody used something like this? No. Of course, a couple of people have mentioned that they have used Boost. So Boost has many of these as well, and has had them since well before 2017. So one of the things about Boost, and that you see in some of the discussions that the standardization committee has, is Boost is often having things much before the standard library. And it's common for the standard library committee to say, oh, this is only in Boost, or it's only here, and we want to have, you know, a little bit more people playing with things out in the field before we're ready to standardize them. And so Boost plays a really huge part in getting things into the library, in that they prove that things are possible. They prove that the libraries are set up in a good way, that the semantics behind them are quite good, and so it's a really great project. And if you're interested in it, you can definitely check it out. All right. That's the end of my talk. I'm definitely a bit early today. If we have any questions, I'm happy to discuss. Yep. I'm not sure that they're prepared to move them into this standard library at all, but I mean, if you're doing graphical programming, then you would have a lot of primitives there, right? Yeah, I think so. Yeah, yeah. The standard library is generally speaking a bit more generic and not towards specific things like that. Yeah. We're still working on it. I've been pulled onto some other projects that I get paid for, so I've put it down for the last little bit because last week I was up teaching in Stockholm, and then yeah, so we need to finish it still. So it's in our list of things to do, and Eric has been on parental, so he got back today actually. So I noticed some pull requests coming in on the Cube project today as I was prepping for the talk. So it'll be fun to see, and hopefully next time I see you guys, I can have a working demo. The demo is a little bit flaky at the moment, so I didn't really trust it to, you know, demos never work when you want to show them off. Some other questions? Yeah. Yeah, as far as I know, they all require 11. I think there's some mention that they use some 14 features, but if the 14 features aren't there, then they automatically fall back, I believe. And I mean, most of these things you could implement with 11 and beyond. So they're made as replacements for the C++ 17 library, right? So things that are new from the compiler side, they obviously don't implement, but if you want to use like variant or optional things like that, then you can use those with the headers. Yeah, so theoretically, no. I can't promise, of course. So in the case of the library that I showed, they actually detect if it's available and they automatically fall back if it's available and don't use their own. So they use the one that's provided by the standard library if it's found. And so I have to imagine if they're going to do that, that they would be quite compatible. The one that we have, that I built, as you can see, I don't have every feature implemented because I'm not using, for example, I don't have value or because I wasn't using it anywhere and I didn't take the time to write it. It would be easy enough to add that yourself. It follows the standard quite closely though. I've tried compiling the code directly with 17 on my local machine, and of course it builds fine there. It's just when I'm building for Android, I can't do that. So like when I'm debugging locally or running unit tests, I can run them directly. And so far, I haven't found anything that isn't compatible.
I would guess that the library you pointed to is only following what the standard says you have to follow. Like for example, for iterator validation and
Yeah,
trust and all that.
yeah,
But if there's any quirks in the implementation that you're going to be using, that's probably not going to work. If you're following the quirks, then probably not going to. You're probably going to crash on that.
yeah. It's quite possible. And the other thing that we have to remember here is like in JavaScript, it's common for them to polyfill future features, so things that will be available in a year or 2 or 3 years or whatever, and that oftentimes those features are not fully nailed down. So maybe the committee decides like, oh, we don't want it to be this way, we want it to be this way, and they change some things, and then you've built something that won't be compatible with the future, so you're stuck with that polyfill. Here we're looking at building in features that exist today. And so the standard is finalized. We know what things we have to support. It's documented quite well. And so that kind of gives us a bit more safety there. Of course, you could take it a step further and, for example, build C++20 features, that sort of thing. Look at adding concepts, for example, that sort of thing.
It's a bit fascinated how you took a pattern from JavaScript and you adapted it into C++. Have you built any other kind of devices similar to that?
Well, like I mentioned about the Docker build, I thought that one was a bit unique because I don't know too many people running C++ in Docker. And I mean, it shaved quite a bit of time off of our CI builds. And so because we're running in Travis for our CI builds, and we're allowed 2 concurrent builds like within our team. And so if you have 45-minute builds, then they quickly stack up if you have a bunch of people making pull requests. So getting them down to a couple of minutes makes a pretty huge difference. Yeah. Yeah.
Anything you're looking forward to in the C++ project?
Yeah, concepts. So when we're doing templating, often we want to know if a type has, for example, a copy constructor or a move constructor or things like that. And so we want to know that it's copy constructible, say. And so with concepts, when we define our type, if we look here, so if I expand this out, we have template and we have a type name in T, and instead of having type name, we can put a concept here, and we can define a concept that this type has to match. So it will only pattern match against things that match that concept. So against something that, like if we have a copy constructible concept, it will only pattern match against something that's copy constructible. And so this gets us a lot of away from the substitution is not a failure type programming that you do in template metaprogramming and tag dispatching, and it means that your templates can be considerably shorter to get things that today take a lot of templating and are very difficult to debug. Yes, very much so. Because one of the downsides with C++ templating is you get, maybe they're not the clearest errors, and you get a lot of errors. So has anybody here seen the Grand C++ Error Explosion contest? And so there's one small piece of code, and it's, I don't know, let's say it's about this much code, and by having some recursion and calling into the template itself, the goal was to make as big of an error as possible from the least amount of code, and they come up with an error that's something like 215 million times as big as the code, just from this little bit of code. So it's kind of amusing, and in the second year, I think they had that you had to get as close to pi digits of error as possible. So it's kind of amusing if you're into that sort of thing. Yep. Some other questions?
Was there anything else from C++ 17 you wanted to use in your code history?
So far, there isn't anything that we're using at the moment, but it's not to say that there won't be in the future. Any other questions? No? Have a beer while we wait for pizza? Remind me to time my talk better. All right. Thanks so much, guys. Cheers.